Hey guys, how's it going? My name is Greg Hogg, and in this video, I'm going to show you how to do LSTM stock forecasting in PyTorch. It's a really important skill and a great way to improve your PyTorch knowledge, so don't click away. It's going to be a really helpful video. I'm going to explain every step of the way, super simple, so let's get started. Now, firstly, I'm just going to get a couple imports out of the way. Really standard stuff, pandas, numpy, and matplotlib for graphing and data frame usage, and torch is PyTorch, and we're getting their neural network module for later. Then we're going to load up our data as a pandas data frame. Mine is called amazon.csv. It's just all of Amazon's daily stock history. You can get that either your own from Yahoo's website, or if you want the exact same copy I'm using, which is what I recommend, you can find that in the video description. You can download that from my Google Drive, and then if you're using Colab, you can go and upload it over here like I did. Okay, let's look at our data set. So if we open our data frame, 6,516 rows by 7 columns. This is daily stock history of Amazon. We have the open value, the highest value for that day, the lowest value for that day, the closing value, which is what we generally care about, and there's an adjusting close and the volumes of shares traded. We don't care about almost all of this basically. We are just going to look at the close column. Now, something that might look a little funny to you is, why is Amazon worth, like, what is this, 9 cents back in 97? No. Okay, so they weren't worth 9 cents. It's that basically to say that this number is that much bigger than this number, well, you have to kind of do a bit of an adjustment on what it was before. Because if you actually go and look up Amazon's IPO value for $18 per share, okay, so we don't see any history of that. We don't see $18 because this is $101 at the very end of this. So basically they do an adjustment because what stocks end up doing is they basically do this split thing where every now and then they'll say like, hey, let's just divide our stock value by 2. And so since it was $200, now it's worth $100. And that's just because they want to keep it kind of standard with other companies. You don't want it to look like Apple's worth 10 times as much as Google if it's actually not. If you didn't understand that, don't worry. I recommend you do some stock analysis because it's actually very interesting for your own daily life. But that's basically the deal, is that they did a bit of a transformation here so that this value is actually representative of it's that much more than it was before. Don't worry about that anymore. Okay, but as I said, we only really care about the closing value. So this is just going to make that data frame only have, well, the date as well and the closing value. So a subset here, and now we have the date, when that was, and the closing value of the stock for that date. This is what we're going to be forecasting. Now remember, on PyTorch, by default, it's going to use CPU, but if you want to use a GPU, which you probably do, you should do something like this, where a device is queued to 0 if torch.queued is available, otherwise you want CPU. And right now, if we output device, well, it just depends on what runtime I'm running. Right now, I don't have a GPU, so it said CPU. Later, when we get to the training part, I will restart it and switch to a GPU, and we'll see that that switches to queue to 0. Okay, now we're going to do some simple transformations. We're going to make the date column a pandas date type, so that's pretty simple. And then we plot the date and the closing value. So over time, we should see here, it goes boom. Okay, so as you can see from before, like this, it's not that Amazon was worth like $1 or 18 cents or whatever it was at this point. It's just a transformation so that it shows that it actually grew this much and then it went lower here. Again, don't worry about that too much. Now I want to set up the data frame in a way that's close to how the model is going to take the input and train off of it. So basically, an LSTM is looking at history. So for one particular date, it wants to know what the closing value was for that date, and the date before that, and the date before that. We can do that with this massive block here, and I'm going to explain how it works shortly. But don't worry about the code here. I'm just going to run that and take a look at this data frame that we produced. We have, for any particular date here, we have the closing value for that date, so it's just close, so that's the same value. Then we have t-1, which means the previous day. So on the previous day, which would be the 26th, this was the closing value. And for 2 minus 2, it would be the 25th. This was the closing value. All the way up to a week beforehand, t-7, we have, that would be on the 20th. This was the closing value. And this goes all the way from this, original value here, all the way up to this, which is the end date that I have downloaded. And so it's the same deal. This is t-1, so this is the value for the 4th. So you should actually see it here, 103.94999. that's that value there. Okay, so it should be in this diagonal format here, where if this is t minus 2 here, well, t minus 2, we go minus 2, and there you go, the same value. That's the closing. Now, the reason our model likes this is because in here we have an input and output pair, or we have an input matrix X and an output vector Y. Here is our input matrix X. It's t minus 1 all the way, all of this stuff. And then here is our output vector. Why is that the case? Well, this vector is what we would use to predict this, because we're looking at t minus 1, t minus 2. We're looking at the last week of history to try and predict what this would be. Now, of course, we know what this is because this already happened in the past, but that's what you use. You use data to try and inform and train the model that, hey, this is our last week, and this is what this next date turned out to be. Now, for this date, this is what the last week of history was, and this is the date we're predicting on. All the way up until our very last data point, we have this is the last week that we were training on. This was the last week of history. And then we're trying to use that to show the model, hey, this is what it was then. Now, the reason that this is informative is because look at the graph. Like in general, if you give it, say, a week of history, it's going to see like, okay, well, clearly in this week here, this was going up. So, of course, the model's probably going to predict that it would go up. Or here, in this week here, clearly there was parts where it was going down. And so the model is probably going to predict that it would go down. We're trying to learn the sequential pattern. This is why we're using a sequential-based model in RNN, because it keeps checking, okay, the price went down again, price went down again, price went down again. I'm probably going to predict that the price is going to go down again. Or if it was going up, the recurrent network updates. It's going up, it's going up, it's going up. Okay, I'm going to predict that it goes up. Now, I don't want to focus too much on the code here, and actually I realized that we're not going to need this duplicate line again. Basically, this function is, it's going to prepare a data frame for an LSTM, where it takes a data frame, like the one we had above. It just has the date and the closing value, so a simple data frame. It's going to take that, and then a number of steps, or basically a look back window. We passed 7, hence we saw we got t minus 1 up to t minus 7. If you instead passed look back is, say, 2, and we run that again, we should see we have very similar things. We have the closing value for that date, but then only up until t minus 2. So I'm going to stick with 7 for this example. I think it's easy to explain, and it just makes sense for the model to have a week of information. Don't worry too much about the fact that stocks aren't running on weekends. This actually does prepare for that. As you can see, there's a jump between well, that's April Fool's Day, so that'd be kind of funny, but there is no April 1st or April 2nd there because that would have been a weekend. But yeah, basically this function is going to make a deep copy of the data frame, and it's going to set the index of that to date in place. And then it's going to do a series of shifts. And I don't want to show you how this works. It's just a complex function, but it kind of keeps stepping where for the number of look back windows, it's going to keep shifting the data frame. And it turns out that if you do it this many times, you step like this, then you're going to end up with this data frame here. I would just copy the code. You could dig it apart if you really wanted to. It would be a good practice for your brain, but not really necessary. So now that we have that data frame, I'm just going to convert it to NumPy. It's the same thing but to NumPy, and it's not going to take the date column. It's just going to have this as the first column because this is set as the index right now. You can kind of see that this is lower because it's not part of the data. So this is our massive matrix, which is shifted df as NumPy. Now remember that since this example is going to predict this, and same thing, this is going to predict this. Basically, this is our vector of outputs y, and this is our matrix of inputs x, so that they line up so that each of these examples is using to predict this. And we're also going to take a subset of this and make it the train, and take the other subset and make it the test. We'll just make the train some first portion, like the first 90 or so percent going up like this, and then the last 10% rows are going to be for the test. Now, before we worry about x and y and train and test, we're just going to run a scalar on all the data. So we'll do a sklearn.preprocessing min-max scalar, and we'll get the scalar is that with the feature range of -1 to 1. We will overwrite our matrix that we have above and just run the transform and fit it on that matrix. and we should see something that looks very similar to the above, except the features are going to be all between -1 and 1. Okay, now that our data is scaled, we're going to make this x and y. So we have x, our matrix x is that matrix above the scaled one, all the rows, but then just the first column onward, because that's this piece here, the first column onward, and then all of the rows, so that massive chunk there. And then y is just going to be all of the rows but the very first column. That's our predictor. And we have x.shape and y.shape should be the same number of rows here, but for x we're going to have 7 different features. Sorry, this is Greg from the future fixing a mistake in my first recording. At this spot, you have to do x is a deep copy of numpy.flip x on axis equals 1, because basically this current data frame here, it has t-1 to t-7. But for an LSTM, you would want it going t-7, t-6 up until t-1, because it's kind of recurringly getting the more updated answer until it gets to the most close to the closed value there is. So you would just want to flip that to kind of mirror this in the horizontal direction. So you're not going to see that in the upcoming cells because I forgot it in the first recording, but make sure you do that. Now we're going to work on splitting this to train and test. We're just going to get a split index, which should be the integer of the length of x, which should be 6509, times 0.95. So this means we're going to use the first 95% as train and the last 5% as test. And our split index, so that's the row number at which we're splitting basically, maybe off by 1, 6183. Now we're going to split x and y into train and test. So x is now becoming x train and x test. Y is becoming y train and y test. And so x should be up until the split index, and x test should be split index onward. Very similar for y train and y test. And these are our shapes, which you should see that these match up perfectly. Now it's a requirement for PyTorch LSTMs to have an extra dimension at the end here. So we're going to do a bit of reshaping to all of these things where the matrices are going to get another dimension at the end, and the y vectors are also going to get another dimension as well. Now so far all of this stuff is in NumPy, but since we're using PyTorch, it probably makes sense to wrap this stuff in PyTorch tensors. So that is really all this does, and makes sure that the values are floats. They're all making them tensors of themselves and then floats. We still should see the shape, but now we'll see PyTorch shapes. They're going to look the same as above. Now, generally when training models in PyTorch, you use datasets rather than just raw tensors. So we're going to make that dataset object now. It's really easy, but to do that, you can't just make dataset of these. You have to make your own custom class, and it's really, really easy. But to do that, we basically just make a dataset, and then we call it whatever we want as our class name, and then you put dataset in there. And we have to specify 3 really simple things. A init, which takes a matrix x and an output vector y, and we're just going to store those in self with the same name. And then we get the length method, where if you call len on this thing, it will return what? It will return the length of x, or also the length of y. That would be the same thing. And then getItem, which is the square brackets thing, the indexing, that just gets x of the index and y of the index that you passed in there. Really, really easy. It just returns that tuple, and that's it. So from that, we are going to make our train data set, one of those passing in x train, y train, and the test with x test and y test. We run that, and I don't need to output anything because they're not really going to output much if you look at them, but just to take a look, it's a data set. One more thing, we actually wrap these raw tensors not in just a data set, but we wrap the data sets in data loaders to get our batches. So we get our data loader here, we'll specify the batch size is 16, and we will get our train loader is the data loader passing in that train data set with the batch size of what we specified, and we want to shuffle that every time. And test, it's going to be the same thing, except shuffle is going to be false. We run that, and here are our loaders. That's where we're going to use to iterate over, get batches, and make updates to our model. Now this next part isn't quite necessary, but for visualization, it's quite helpful. We get for underscore. Later we'll keep track of something else. Don't worry about that. We're basically just looping over and getting a batch from the train loader. And we get the x part of the batch, and the y part of the batch is, well, the x batch will be batch sub 0, and the y batch will be batch sub 1. But we have to convert those or put those on the device that we're using. Later, when we make the model, we will make sure that the model goes to that device as well. So we put it to either the CPU or the GPU, And then we're just going to look at the X batch shape and the Y batch shape. What are we expecting? Well, since the batch size is 16, and what are we looking at for the inputs? Well, the inputs are the X should be 7 by 1, and the outputs should just be 1. Okay, so we are going to see that we have our size of 16 by 7 by 1. We have 16 examples where we have the 7 look back window and then just that extra 1 there. And then for each of those look back windows, we have our predicted output, which is just one value. Here's where we create our model. In a moment, I'm going to paste a ton of code on the screen, so don't feel bombarded. I'm going to explain it every step of the way. But let's be honest, this is confusing. It's a confusing model, and LSTMs in PyTorch are just more annoying than they are in TensorFlow. Of course, like most trade-offs here with PyTorch and TensorFlow, TensorFlow is a little easier for beginners, but PyTorch is a little more flexible for people really in the field. Here, it's going to look pretty confusing, but let me try my best. So here's our code. We have a class LSTM neural network.module. It's going to take in the input size, which is our number of features. We'll pass that a 1. Hidden size, which is however dimension we want to be in the middle there. Could be 1, 2, 4, 32, the same type of thing in a linear layer. And number of stacked layers, which is basically you can stack LSTMs because as they recurrently run through themselves, they're going to produce a sequence themselves. They'll produce a sequence of hidden layers. And so you can stack these things if you want. If that didn't make sense, I would check out Andrew Ng's courses if you want to hear about that. Otherwise, just take it as the more of these things that you have, the more complexity that your model would have. So we're going to do our standard super init. We'll get to the hidden size is the hidden size. Our self.numStacked layers is the numStacked layers. Then we don't need to keep track of the input size because it's just where we create our LSTM part. So the LSTM part of the model is going to take in input size, which again is just the number of features we're looking at. It's just going to be one thing because we're just looking at the closing value. The hidden size, whatever we define for that, we're actually going to end up passing 4 of those. And number of stacked layers, again, I'm just going to give that 1 because it turns out that this model is going to overfit pretty well anyway. So we're just going to use one of those. And batch first is true, which means that in some later pieces, you'll see that it returns the batch as the first dimension. Finally, after your LSTM, it does the recurrent part for taking in the sequence. You would want a fully connected layer, which is going to map from your hidden size, whatever that hidden layer was, to just 1, because at the end of the model, you need that to predict just your final closing value. So that's why that's a 1. Okay, and then what your forward function does is going to look extra confusing, if that wasn't already confusing enough. We have the batch size, which is x.size sub 0. So you have to kind of dynamically get this size from the input. That's important. And then we have h0 and c0. Man, what the heck are these things? Okay, so if you go to look at an LSTM, they have a couple of these gate things, these gate vector-like things. And I don't want to get into the details, but basically you have to kind of initialize the LSTM by passing it these default H0 and C0 things. And they have to have this particular shape, and they also have to be on the device that you're working on. I do not want to get into the details. It looks like this, and you initialize these two things, and then you're going to pass them in this tuple here when you go to use the LSTM. So you get your output that you actually care about. You get your updated tuple of your H0 and C0, which we're going to ignore because we don't really want that. Basically, after you pass X in here, it will give you your output. And then furthermore, output is not actually the output that you'd expect it is. You get output from passing in. Well, of course, you have to do your FC layer, but then it's out from :(-1:). Right now, I am not digging into the details of why that is the case. Trust me, it is going to work. We create a model where we're passing it. We have one feature, just the closing value. For hidden size, you could play around with that if you want. Numstacked layers, you could also play around with that if you want, but just one will be fine. We will create our model, put it to the device, and here you go. In the same format that I did in the first tutorial, I want to first show you the training loop using functions we haven't quite written yet for train an epoch and validate an epoch. And in a moment, we'll write those functions. Although I'm not going to go into them as much detail because I covered them a lot in the first video and we played around with it a bit in the second video. So I would check those out if it's a little confusing to you. But we're going to specify our learning rate. We'll start this at 0.001. Number of epochs, we're going to make this 10. Loss function is the mean squared error. That might look a little surprising, but this is basically a form of regression problem. We're still predicting a continuous value, and so we are going to try and minimize the mean squared error. Our optimizer, we're just going to use the standard atom by passing the model's parameters and the learning rate that we adjusted. And then for epoch, in the range of the number of epochs, we are going to train for an epoch and validate for an epoch. Now let's write our train function. Okay, so making sure to put this above our training loop here, we have train one epoch, which is going to set the model to training mode. We will print the epoch and we'll start to accumulate this running loss value. Then we're going to loop over the train loader. So this basically just gets a batch and keeps track of the index. And we'll get our X batch and our Y batch from the batch and put it on the device that we're using. We will get our output, which is getting our output from the model. So we put in our X batch into the model, that gets our output, and we get our loss is the loss function of the output and comparing that to the ground truth. So comparing our model's outputs to the ground truth is our loss value. Then we get the running loss is plus equals the loss dot, this should really be dot item, but it doesn't really matter. Basically, the loss is just a tensor with one value. And so we will get item, which just actually gets the value from that tensor. So running loss plus equals the loss dot item will accumulate that loss. And then we zero out the gradients. We do a backward pass through the loss to calculate the gradient. And then we take a slight step in the direction of the gradient to make our model just a little bit better. Then every 100 batches, so this says if the batch index mod 100 is 99, so at the 100th batch or every 100 batches, we will get the average loss across those 100 batches is the running loss divided by 100. That'd be the average. And then we print the batch and it should be the average loss for the batches, but we just write loss is well, we're just printing that. And then running loss should be reset back to 0 so that that's proper. We will execute that, just create the function, and now let's make our validate function. So putting this above our training loop again, and we'll put it below our train, although it doesn't really matter. Here, we set the model train to be false, so basically put it in evaluation mode. We specify our running loss starts at 0, and then the batch index and the batch is going to enumerate the test loader. So we're going through getting batches from the test loader. There's our X batch and Y batch. And then with no gradients, we don't need to calculate a gradient because we are not doing any model updates, so we don't need those. We get our output is just putting that X batch through the model. We accumulate our loss we get our loss by the loss function is comparing the outputs that we got to the ground truth. We accumulate our running loss by, again, I would make that accumulate the loss dot item. We get average loss across batches is the running loss divided by the length of the test loader. So across all the batches, we get our average loss value. And so we can print that down there. We will run that. And then let's quickly just check if this works. It is working. And we should probably train with the GPU, although actually it's pretty fast. No, actually, okay, fine. We're sticking with CPU for this lesson because, the model already overfit. So let's take a look. So you can see the loss was very high at first, but it very quickly figured it out. So it goes down, validation loss goes down, and yeah, this seemed to train just fine. It actually was perfect, and I mean it was on purpose because I had set this to 10 epochs. If you were training your own model, you would of course always have to play around with the learning rate, the batch size, the model architecture, but I'm setting this up so that this works right away. And yeah, let's carry on and let's look at our model. Okay, this is just some code to do some plotting. So we're going to do no gradients when we get our predictions. So we'll get our predicted for the X train. So this is for putting all the X train stuff in to get our predictions for the first 95% of the data. Remember, the model's already seen this stuff, so it should do pretty well. But the model takes that in, make sure that it is on the device when you're putting it into the model. And then you have to put it to the CPU in particular. That's not a typo, because after you convert it to NumPy, well, NumPy doesn't use the GPU, so the stuff that you're using better be located on the CPU. So we put it there. So we get our predictions for the first 95%, and then we plot the Y train is the actual closing compared to our predictions for that, and then we plot the day and the close, and we should see our graph where the orange is the predicted and the blue is the actual. Remember, the model's already seen this before in training, so it should be pretty good. But you see the day as it goes on, and the closing value, whoa, is a value from -1 to 1. That's just our scaler. So remember, we scaled this data on purpose, so it's all in this small range for the network to use. But we're definitely going to have to use an inverse transform in a moment because we don't want to look at these values. It just looks weird. Now this next piece might be a little confusing, but I'm going to take it really carefully here. We have our values between -1 and 1, so we need to do the opposite of what our transform did so that we get our original scale back, the real numbers or dollar values that are actually useful to us. Now it's not too bad, but there's a little bit of a trick that we use. Now train predictions is going to be predicted.flatten. That's not a trick, I just making sure that it's one axis, that's important. And then dummies. Why am I calling this dummies? Well, it's a zeros matrix, and we'll look at it in a moment. But basically, I don't care about what most of this stuff looks like. It's really just having the proper shape, and then we're going to adjust the first column. So dummies is the zeros, where it's the shape of the X-train shape sub 0, so the number of examples that we have. And then our look back plus 1. It's look back plus 1 because that is the length of this whole thing. Okay, so I'm trying to make a dummy matrix that looks like this. So look back plus 1, well, this is 7. So look back plus 1 should be 8. So it's the same length here. And then it's going to be the row-wise the number that we have in X-train. So why am I making this weird dummy matrix? Well, it's so that I'll set the first column. This sets the first column of that to the predictions that we have. And then we can apply our inverse transform, because our transform is used to taking that whole matrix. And maybe, I don't know if you guys know an easier way to do this, maybe there is, but basically I just made a matrix that has the same shape as what the scalar was used to, and then I did an inverse transform on that whole thing so that we can, again, just care about the first column, so it actually transformed that first column well, and then we'll get back our train predictions in the right scale. Is we're going to get a deep copy of that dummy's first column again, that transformed column. And train predictions is only that first column that I'm selecting. And here you go. You should see early values should be very small numbers like we saw, and high numbers should be, or later numbers should be high numbers like we saw. Now we're going to do something very, very similar for the ground truth. This was for the predictions, but now for Y train, since that's also currently on the wrong scale, we get our dummies is our matrix that looks basically the same thing. Dummies is that first column is now going to be Y train.flatten. So we update that first column, apply the transform on that whole thing, and then we get new Y train. It's just going to be a deep copy of that updated first column, and we should see Y train there. Now we're just going to make the same graph. It's exactly the same thing, except we have new Y train there, and train predictions should be the same as before. Looking at the close, oh, sorry, those are backwards labels. This should be day, and that should be close. So here you should see the day on the x-axis, close on the y-axis before, except now they're on the proper scale. So the graphs, they shouldn't really change or look any different. It's just that they're on the proper scale now. Now we need to do this for our test stuff. Now I'm going to do this all in one chunk here. Before we kind of looked at this intermediate graph, which was we had on the wrong scale. I'm just going to show you how to get the test predictions and convert them to their proper scale here. And I'm purposely using slightly different code just for PyTorch to get different practice with different functions that do similar things. That's a lot of wording, but just take a look. So test predictions is you, again, get your X test and you put that to the device the model's on. You get our outputs. Then we do .detach, and you'll notice, oops, not that. You'll notice there's no torch.nograd here. This is kind of an alternative in this situation where we detach this from the computational graph, then we put it on the CPU, then we can do NumPy, and we're going to flatten that as well. So it's a very long chain of these things, and that's not, unfortunately, not uncommon in PyTorch, but it gets the job done. Basically, it is just a vector of our test predictions. If you were using TensorFlow, it genuinely would just be like you just run them through the model, but that's what it is. Dummies is the same thing as before, so I'm really not going to explain that. We are just going to convert our test predictions to the right scale, and we'll run that, and you should see the proper scale on the test predictions there. Now we just need to get our ground truth on the proper scale, but this time it's for y-test. I don't want to explain this because it's basically the same as it was for y-train, and now we have new y-test on the new scale. And let's just finish this off with our final graph. So this should be our new y-test, our ground truth that the model kind of seen like it hasn't actually seen it. It just evaluated through it, and our test predictions as well. So on the proper scale, we have our actual and our predictions. We have, this is probably, okay, this is the right labels this time, day and close. And here you go. Okay, so after, this is the part that occurs after this piece here. You could optionally do some extra work to get what these particular days are, although it's a little bit annoying, so I'm not going to bother doing that. Good practice if you want to. This is what the model did. So you can see it's kind of just lagged behind it. It's following it pretty well. It's hard to do forecasting well, like stock forecasting. If you were to actually get a really good job of this, then you should go to Wall Street. To be honest, that's uncommon. And what you should not do is think that the model that we just created is for predicting stocks the next day. You will almost certainly lose money if you do that, and if you even make a more complex model. Of course, people do it. It is kind of crazy though. Most importantly, if you are doing stock forecasting, think about the intrinsic value of a company. Think about the current state of the economy. If there's a lot of negative news and it's been down a lot recently, actually it's going to go opposite most likely, and that would be a time for it to go up. Conversely, if it's been going up for a long time, it's probably just going to go down. And most of these stocks work well together. Occasionally companies have fallouts and they have issues, but for the most part, if Amazon's doing well, so is Netflix, Facebook, Google, Apple. All of them kind of work well together. So that's the sort of stock analysis you should do. Nonetheless, here is our LSTM stock forecasting model. I hope that this was helpful. It's a really useful skill to be able to do stuff like this. Feel free to try out other models, like maybe a GRU, maybe a linear model, whatever you'd like to do. If you're not subscribed to the channel, I'd recommend doing that. Awesome idea to do. Drop a like on the video if this was helpful. And yeah, I'll see you later, guys. Bye-bye.